some errors Einstein made in his theories of relativity. This is not criticism against Einstein only, but Albert Einstein has become a household name. The history of relativity has been rewritten by historians of science, and in a rather bad way. I've listed here names of people. Do we know who Max Abraham was? Fritz Hasselhoff, Walter Ritz, Oliver Heaviside, Joseph Larmor, Kurt Mosengeil, A. Robb, Henrik Lorentz, we know, but not for his theories of electron, and Voigt. These names have been attached to relativity, and they've somehow been removed. And this is what I wanted to discuss this morning. Wanted to start with the enunciations of Einstein on his principles of relativity, and most important of all, the name that's missing here is Henri Poincaré. Poincaré is known as a mathematician for about everything except relativity. And Poincaré just happened to be that person who 10 years prior to Einstein came up with these principles. And according to him, the laws of physical phenomena should be the same whether for an observer fixed or for an observer carried along in a uniform translation, so that we could not have any means of discerning whether or not we are carried along in such a motion. First principle. Second principle, light has a constant velocity, and in particular that its velocity is the same in all directions. Now let's compare those with Einstein's. 1. The same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold. 2. Light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. Many historians of science have criticized Poincaré because Poincaré added a third principle, and that is contraction. Okay? That is, when the bodies travel at the speed of light, they somehow contract according to Lorentz and Fitzgerald. This contraction we haven't seen so far, but according to relativity theory, it predicts this, and we'll see why. So, this is the criticism lodged against Poincaré, and the other criticism was that he didn't give up his the concept of an ether. That is, to 19th century physicists, the ether was all important. You needed a medium in which to propagate things. Sound won't propagate if it doesn't have a medium to propagate in. Light somehow doesn't need that medium because it's self-oscillations of electromagnetic fields themselves. But to 19th century scientists, they needed an ether. And this was very hard to give up, especially Lorentz, and especially Poincaré. So this criticism lodged against them showed that Einstein didn't have these problems, that he gave up the ether, which is not true, we'll see, and that the third principle was not necessary because it's contained in the first two laws. Now, Poincaré, if we look at Poincaré, when he elevated c to a constant, c is equal to the distance traveled to the time involved in the propagation. Okay? Velocity. No problem. We measure velocity as meters per second. Okay? So meters per second is what we give it. We need a National Bureau of Standards to know what a meter is. If the National Bureau of Standards disappeared completely, we'd have no means of determining what a meter is. So Euclidean geometry, which is what we're involved in here, is relative. By elevating c to a constant, a universal constant, independent of its value, what we're doing is we're eliminating these definitions of meters and seconds. Constants absolute constants only appear in non-Euclidean geometries. They don't appear in relative Euclidean geometry. So by using an absolute constant, which is related to the curvature of space, what they were doing was elevating, they were removing relativity from Euclidean space and putting it in non-Euclidean space, which they objected to because, according to Poincaré, it is Euclidean geometry which is the most simple geometry. And if we have to change the laws of physics, we will do so in order to salvage Euclidean geometry. This was expediency, not anything that anything deeper than this. And we will see why it can't be so. So, in the most celebrated paper of Einstein, the 1905 paper, in section 2, we come out with the definition of velocity, and we also come out with, consider that is, Poincaré always used light signals for transmitting and receiving. This was a way of measuring distance and also to measure time differences. So if we have a light which is emitted at A, goes to B, the distance between the two of them is RAB. This is Einstein's notation. And we have TB minus TA, which is RAB, divided by C minus V. If we're going in the direction of the ether. Coming back, TA, we arrive back at A at a time t prime, minus TB, and this is equal to RAB plus C plus V, if we're going in the opposite direction. Okay? Well, here he's considering emission theories. That is, that light, when it is emitted, depends upon the speed of its emitter. Okay? It's like riding a train and shooting a projectile from the train. The projectile's velocity is that of the projectile plus the train's velocity. Okay? But if light is to be considered has a special constant associated with it, c, this can't hold. And this gives rise to many adverse effects, like the contraction. Okay? And these emission theories, what's wrong with these emission theories? To do experiments, like the Michelson-Morley experiment, they're round trips. You got to go back, forward, and then come back again. The same types of, if you look to the stars, it's not that same way. That is, emission theories can be disproved. For example, consider a binary star. And this is what de Sitter did in 1913. If the binary star is rotating, light from one side of the binary star will arrive at Earth at C plus V. The one that's when it's going away. When it's coming, the other side of the star will be C minus V. And in some place in time, the two of these light rays would interact. Okay? And he looked for interaction. That is some type of optical phenomena which would show that these emission theories would hold. That is, if light was not emitted with a velocity c at both sides of the star, binary star. And he couldn't find any. But then there are what they call emission theories. They're extinction theories, which means is that no matter how rare space is, it is still has a density, and that the wavelength of light should be affected by the medium in which it travels. So after one or two extinction wavelengths, you shouldn't see anything. So this discussion has been going on for many years, but most people believe that emission theories do not hold. So in this sense, if we look at RAB, we solve this for RAB, the distance between the two, times TA prime minus TA. So here we see, in the round trip, going out and back, there is a contraction of r due to the motion. Okay? And this was the same problem they had in the Michelson-Morley experiment. Fitzgerald, who I didn't include here, hypothesized that there must be some type of contraction motion in order to render equal the two arms of the interferometer, one in the direction of the ether and one normal to the ether. I'll also say that all earthbound experiments are only good to the square of the ratio of the velocity to the velocity of light. This is not true for interstellar. That is, when it comes one way, you can get a first order effect. So what we would conclude from this is that clock B goes slower than clock A by v squared over c, or the opposite, clock A goes slower than B by the same amount. So which is it? So many years people have been thinking about these things and have invented types of gedanken experiments, which are oxymorons themselves, because you don't get anything out of a gedanken experiment that you don't put in. And there's things like the twin paradox, where one of the two brothers goes up into a space capsule, travels around, comes back to Earth, and sees that his clock has been running slower than his brother's, and that he's aged less. So in the 60s, there were titles in newspapers, "Space travel will make you younger," things like this. And this caught on to the general public. That is, these things like this. But who traveled? The person that went into the space capsule, or the person that remained at Earth? Because he's still moving too, it's all relative, one to the other. So you can't say anything. Plus the fact there are accelerations involved, because he had to go out and come back. So going out and coming back, he had to slow down and speed up again. But relativists will say, no problem, that even acceleration has no effect on the velocities if we consider infinitesimal time intervals. This is not true. So the thing is that people have been looking also at models. How can we understand things like this? So a person called Herman Bondi, who took it from Withrow, who took it from Robb, without, this is what they call nostrization. Making it your own. Bondi didn't realize, give any idea of where it came from Robb at 1911, where you have Tom, you have Dick, and Harry. Okay? And you want to do away with accelerations. So Tom is stationary, and Dick is moving at a velocity v in this direction. Harry is moving in the opposite direction with a velocity minus v. And Tom synchronizes his clock with Dick's at a time t0. Okay? And at a later time, Dick synchronizes his clock with Harry at a time t1. Okay? Now the only thing that we have to assume here is that when the person is moving away from us, the intervals of emission, that is called the interval of emission I. So when he's moving away, this will be magnified by a factor of k. When he's moving towards Tom, Harry, the interval will be the opposite, 1 over k. Okay? So this is at the interval at which they arrive. Now, the distance from, say, t0 to t1 is t0 plus v t0 divided by c. Okay? This is the distance traveled. This is the velocity at which it's traveling, photons. Each of these have guns, photon guns, which emit photons. Now, the thing is that this is what Tom will see. And this must be equal to the interval at which it's being emitted times the number T1 over I of photons in this direction. So Harry, Tom now will see, since Harry is coming towards him, V0 T0 divided by C. The interval will be 1 over K times T1 over I. Okay? Obviously, the interval doesn't make any difference at which photons are emitted. And we can do two things with this now. We can multiply them together, and if so, we come out with T0 squared, 1 minus V squared over C squared, is equal to K, is equal to T1 squared. Okay? Showing that time now has been contracted. Or we can divide the two of them, and in which case we have 1 plus V over C, 1 minus V over C, to the 1/2 is equal to K squared. K. Okay? This is time dilation, lengthening of time. This is the first order Doppler effect. Okay? Which of the two is more important for this thing? According to a person called Essen, Louis Essen, the inventor of the cesium clock, that T0 should be the same as T1. In which case, if I add a factor of alpha here to both of these things, of alpha squared, and alpha is the decrease in the emissions of photons, because if the photon, if Tom measures photons which are coming at him, which is reduced, there will be a factor of loss of ticks someplace. Ticks are being lost. This is according to Essen. I don't think this is a proper interpretation of it, because I just leave it as time dilation. Okay? Now, let's do the same thing now, looking at the Lorentz transformations. Okay? I have X. If gamma were 1, that would be just Galilean. And T equals T minus 4x over C squared. In Galilean terms, this would be equal to 0, and gamma would be equal to 1. And these would be nothing more than absolute time. If we square this, multiply this by C and square that, we come out with the invariancy of the interval, okay, which is comparable time dilation. If we divide the two of them together and define velocity as x minus t equals v, which is equal to x over, we come out with I will call this one u. This would be u minus v over 1 minus u v over c squared. This was first written down by Poincaré. Later it was generalized by Einstein when there was a difference, angle difference between the two Lorentz transforms. That is, that there were two different planes. This was generalized by him in 1905. But the original one was Poincaré. If you put in c for u, you come out with u prime is equal to c. This can no longer surpass the velocity of light. Okay? No matter which I choose to put c in. This would be the non-relativistic addition of velocities. And this is the relativistic deflection velocities. Now, back in 1909, Arnold Sommerfeld looked at this analogy with the analogy of hyperbolic functions. The hyperbolic tangent of a plus b, or a minus b, say, equals tangent of a minus tangent of b over 1 minus tangent a tangent b. Okay? Looking at the analogy of these two, I would just have to write v is equal to c tangent of some other v over c. Okay? This other v over c is a hyperbolic measure of the velocity. So as the hyperbolic tangent goes from 0 to 1, this is the ratio of v over c, the v, other v, would go to infinity. So the idea was that these new measurements done by Opera and CERN would be that the v they measured was not the Euclidean v, but the hyperbolic measure of the velocity, v. Okay? Now, the thing is that if I take the logarithm of this, of both sides, okay, I have 1/2 logarithm of 1 plus v over c, 1 minus v over c, is equal to the inverse tangent hyperbolic of v over c. Okay? And this by itself would be precisely the length tangent, about tangent of v over c, is the Lobachevsky segment of length in hyperbolic space. So all this goes to show it's not space-time which is important, but space divided by time, or the velocity. And all this, as far back as 1909, could have been written down, was written down by Sommerfeld, and then quickly forgotten by the Gothic mathematicians. In a note published in 1910, Kaluza, another name, known to string theory, suggested that the metric was not the metric that you write down for space, is dr squared plus r squared dv squared, if this is Euclidean, okay? If it is elliptic, it would be dr plus r squared and if it was hyperbolic, it would be dr squared plus this is the hyperbolic sign. R0 is related to the absolute constant, which in this case would be c. R would be the velocity, and if we go to a uniform disk, it would be r omega divided by c, would be the velocity. So in this case, dr squared is dr squared over 1 minus r0 squared. This is a stereogeographic factor which comes in due to the bending of space. Okay? Now, before leaving this topic, it's interesting to see that if I do the same thing here, and write this r squared, 1 minus r divided by r0 times d squared I consider a disk, a uniform disk, and spinning uniformly with an angular velocity omega. This would be c squared here, same thing here. I consider the radius constant. This term would go away. And now I'm looking at ds is equal to r d phi over 1 minus. And I can integrate that from 0 to 2 pi, 0 to 2 pi. This would be the circumference of the circle, and this would be equal to r 2 pi over 1 minus r. So the circumference has become larger by this factor. So this was one of the predictions. Einstein was infatuated with a uniformly spinning disk. And he argued that if I lay rulers in the direction, in the radial direction, there should be no change. But if I lay the rulers tangentially, according to this, there should be a Lorentz contraction, and the disk should be larger because I need more rulers to lay tangentially around. But this is incorrect because if the rulers contract, so will the circumference contract. And I can't have any effect like that, observe any effect like that. In fact, if you call the inhabitants of this disk Poincaré's, little two-dimensional beings, they walk around with clocks and rulers. And as they walk around the disk, their rulers will shrink or increase along with their bodies. So they can, and their heartbeats. So they have no means of distinguishing where they are on the disk. If they can communicate with each other, there is no way of telling where they are. And one of the most famous gedanken experiments of Einstein was to put a local observer on the edge of the disk and another at the center. The center, obviously, is an inertial frame. So his clock will be running normally. The clock on the rim of the disk will be slower than that, and he will communicate that to the observer located at the origin. This is impossible. Two local observers can never communicate. It's all a matter of reference. To us Euclideans, we would see the distortions in these factors. But to the people living in the hyperbolic world will not see any difference in the measurements that they make with their clocks or with their rulers. So, another problem was that if I write now this metric, so factor g squared minus some r squared times another 1 over g squared, with g depending upon r. This would be a metric which would be a generalization of this one here, due to the fact, according to Einstein, that there would be acceleration. Now, this is divided into two parts. One is the spatial part, and one is the temporal part. Back in 1912, Einstein, who more often than not contradicted his own principles, was looking at the bending of light. Okay? Leonard, whose name is associated with the photoelectric effect, was very anti-relativistic in the analogy, pointing to the fact that the deflection of light by a massive object was done back in 1804 by a person called Solder. And the story goes that Einstein came up with a certain, due to the deflection of light in 1912. Thank heavens, the war, First World War, was approaching, and they couldn't get to Russia to do the observations. Only after the war, Eddington went to did the South Atlantic, did it, and found that there was a factor of 2 difference. Okay? The deflection of light, the advance of the perihelion of Mercury, were two of the most important results of general relativity. They are static. The other one is the reddening of wavelength, reddening of frequency in a gravitational field. I want to show you how Einstein obtained his first result. He began with nu is equal to nu 0, 1 minus v over c. Okay? This is the frequency of the emitter, this is the receiver, due to velocity v. Okay? He replaced this, v is equal to g times t. G is the gravitational acceleration on the surface of the Earth, nu 0 equals. Okay? Then he considered a photon being emitted at a certain height, falling and being reabsorbed in a height h. He replaced t by h over c, and this becomes c squared. So now we've gone from uniform velocity to constant acceleration here, and we can go one step further. We can say that the acceleration times the height is minus the static gravitational potential. Okay? So we've come a long way from uniform velocity, uniform acceleration, to a static potential. Now, what does that static potential operate on? Well, according to Einstein, C is equal to C0, 1 plus V over C squared. But he just told us several years back that C was a constant velocity and not one in which varied with a position in a gravitational field. At the center of the coordinate system, we have C, 0. If we move out, we have C. So a clock will be, we must employ a clock which, when removed from the origin of the coordinates, goes 1 plus V over C squared more slowly than the clock used for measuring time at the origin of the coordinates. We will call C0 the velocity of light at the origin of the coordinates. Then the velocity of light at the place where the gravitational potential will be given by C. All I see here is a cubic equation to be resolved for C. Don't see anything else besides that. But then he goes on. The principle of the constancy of light holds good according to this theory in a different form, that which it usually underlies the ordinary theory of relativity, he says. But he doesn't tell us which way. So here he's negating the fact that C is an absolute constant. Okay? Then he uses Huygens' construction of the propagation of disturbances, waves. If I drop a pebble into the pond, I will come out with wave fronts. Okay? And he considered the normal to these wave fronts and introduced the normal derivative with respect to the normal is equal to C0 over C squared divided in the n. And he calculated delta deviation 1 over C squared times theta equals minus pi over 2, theta equals pi over 2, Gm, m is the mass of the sun, r squared, r indeed theta, this is the arc length, and he came out 2gm over r C0 squared equals 4 times 10 to the minus 6, or 0.83. Okay? This is the deviation due to the light in a gravitational field. This is 1911. 1915 doubles that to 1.75. Okay? It's not, the important point is, it's not the factor of 2 which is involved, because Walter Ritz, calculated the advance of the perihelion of Mercury back in 1907. And he allowed for parameters to come in, which had to be fixed through observation. The problem is getting a theory which is consistent. Okay? So the thing is that another point would be, from the historic point of view, Einstein was given the Nobel Prize in 1921 for the discovery of the photoelectric effect. Okay? Electrons are being emitted from surfaces. It depended upon the potential difference and the frequency. And one of the historians of science, a person called Abraham Pace, who wrote Some is the Lord, said that that the energy should vary linearly with nu. Second, the slope of energy versus frequency plot is a universal constant, independent of the nature of the irradiated material. Third, the value of the slope was predicted to be Planck's constant determined from the radiation law. None of this was known then. This gives the impression that Einstein single-handedly discovered the photoelectric law. This is certainly not true. Thomson, J.J. Thomson, the discoverer of the electron, who wrote in his 1928 book on electron discharges, it was first uncertain whether the energy or velocity was a linear function of the frequency. Hughes and Richardson and Compton were, however, able to show that the former was correct. The relationship between maximum energy and the frequency can be written in the form the kinetic energy at which the electron is emitted is equal to the energy at which it's activated minus V0 E, where V0 is the potential characteristic of substance. And this is the sentence which is important. Einstein suggested that K, this K, was equal to H, Planck's constant. Okay? So, this was what Thomson had to say about it. Also, the thing is that people, the olden days, were worried about relativistic mass. Okay? That is mass which increased with velocity. Mass would increase. This was the Lorentz model. Lorentz. Einstein model. Then there was another model put out by Abraham, and still a third model by Buchner. Okay? They differed. One was a prolate ellipsoid, but they thought that the electron in rest should be spherical. Then, when it is in motion, it becomes deformed due to the motion. It's the Lorentz contraction. So the difference between the Lorentz-Einstein model, Abraham's model, was the difference between a prolate ellipsoid and an oblate ellipsoid, a pancake versus a cigar. Okay? In the end, this one made it. That is, the deflection experiments, that is, what they did was to send electrons through electric and magnetic fields, cross magnetic fields, and they observed the deviations. From this, they could determine the more it deviated, the greater the velocity was. Okay? So this, first of all, seemed to apply only to charged material. Okay? But at this time, people were interested in showing that the total mass was electromagnetic in origin. Okay? But the fact is that neutral matter should have no effect at all. So what Einstein did was to say, I can always add even a small amount of charge to any body and make it a charged body. This doesn't sound very convincing, but the fact is that he generalized this mass, charged mass, to all mass. Okay? Now, how does something like this arise? Well, we don't even need to talk about mass at all. We can go back and talk about Doppler effect. Let us consider the average Doppler effect going in two different directions. So, the shifted frequency going in the positive direction, and the shifted frequency going in the negative direction. And I will call this the change in the frequency, which is mu 0 divided by 2. 1 plus mu over c, 1 minus mu over c, minus the opposite, the inverse. And this is equal to mu . Now, what was known at the time, this is mu 0, and this is delta mu. Now, what was known at the time was Planck's law. So in this case, I multiply by h, divide by c, I multiply this by h and divide by c. H mu 0 is the change in the energy, delta E, or E itself, sorry, the energy, divided by c squared, V divided by. And I get this. But E divided by c squared is just m, the rest mass. And this is nothing more than the generalization of momentum. Okay? So here, this G was calculated by, again by Poincaré, for the recoil of an artillery piece which shot out a cannon. So here I've gone from a Doppler effect in the frequency to the energy to the mass increase. I don't even have to just discuss mass increase. It's all included in this. So this is one way of obtaining the relativistic increase in mass. At the point 1905, Hasernoyer showed that the energy was 4/3 mc squared. The 4/3 came in a very strange way through the Lorentz transform. Okay, it is due to a pressure which is called the Poincaré pressure, because the transformation of energy in the Lorentz transformation is not the transform of energy, but the transform of enthalpy, H, which is E plus PV. PV for a relativistic gas is equal to 1/3 E, and we come out then with 4/3 E. Okay? This 4/3 interested a lot of people, but Einstein couldn't care about it at all. In a relatively unknown paper, though, Einstein comes out with trying to distinguish between the longitudinal mass and the transverse mass. What does that mean? That means that if I take Newton's law, F is equal to ma, m is the mass I put in, it's the transverse mass. But there's another way of defining the force, as a derivative of momentum. And here I will have dm in dt plus m dv in dt. Another contribution. And that contribution was longitudinal mass. The only point is that Kaufman's experiments did not pick up longitudinal mass. So this was subsequently swept under the carpet. But Einstein comes out and tries to design an experiment to distinguish between the ratio of the longitudinal mass to the transverse mass. So Einstein was not at all attached to his own principles. Okay? Also, talking about the ether, there's another interesting story. 5 years after he finished his theory on general relativity, he was invited to Leiden in honor of Lorentz, who he respected a great deal. And there is he had to give a seminar in May, and he said this about the ether. The whole change in the conception of the ether, which the special theory of relativity brought about, consisted in taking away from the ether its last mechanical quality, namely its immobility. According to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. Space without ether is unthinkable. For such a space, there will not only would be no propagation of light, but also no possibility of the existence for standards of space and time, that is, measuring clocks and rods, and therefore any space-time intervals in the physical sense. But this ether may not be thought of as endowed with a quality characteristic of panmedia, as consisting of parts which may be tracked through time. The idea of motion may not be applied to it. He needed this because of the fact that he tried to explain gravity as a geometrical effect, and geometry was space. So space would have an effect, like an ether. So essentially what Einstein was saying, what wasn't good for the goose is good for the gander. That means that what was eliminated in special relativity crept in again into general relativity. So here again we have contradictions in what he said.